Hey there, stats enthusiasts. Welcome back to our AP Statistics series. My name is Goldie, and today is going to be our first video in Unit 6, Inference for Categorical Data, specifically proportions. This unit is going to introduce confidence intervals and significance tests and lay them all out for proportions. This is Notes 1, so it's going to be an introduction to confidence intervals. We're going to learn all about confidence intervals, confidence levels, critical values, all the exciting things that get wrapped up into it. So let's go ahead and dive right into today's lesson. We're going to start today by going over some of the basic information about confidence intervals. Like, we're starting from the bottom. Here is confidence intervals 101, okay? So if we want to estimate the value of a parameter, P, so specifically talking proportions, we know that we don't always have information about the population, and a lot of the times we want to collect data to determine what our population parameter is. So if we want to estimate it, the best way to estimate it is by taking a sample and then using our sample statistic, which for proportions is P hat, in order to estimate P. So that's why we take samples in the first place, right? Is because we want to find out information about the population. But we know through our conversations that when we select different samples, we will have different values of P hat. And therefore, every time we select a sample, we're going to get a different estimate for P each time. So what we want to do is have a reliable estimate for our population parameter. So a lot of the times, just a single estimate isn't going to be as reliable as, let's say, an interval of estimates. And that's where a confidence interval comes in. It's going to give an interval of plausible values for our population parameter based on the information we get from our sample statistic. So that's where confidence intervals comes in. It's an interval of plausible values for an unknown parameter value, which again is what happens in real life, right? We don't know what our parameters are, so we're going to take a sample and figure that out. So for our population proportion P, we can estimate its value using P hat as our point estimate and constructing a margin of error around it. So that P hat value we get from our sample, that's going to be the middle of our interval. So the way we start constructing this is we take that point estimate and we plus or minus some sort of margin of error. And a few things go into this margin of error that we'll be talking about, but that's the skeleton of a confidence interval. We have our point estimate in the middle, and we go up a certain margin of error and down that same margin of error on either side to get an interval. And the way we present this interval, there's a couple different forms. The first form is actually the point estimate plus or minus that margin of error. So if our point estimate is 0.55, we would do plus or minus 0.15 as our margin of error. So you might see a confidence interval given like that. You might actually see it as an interval notation. So to get 0.4 and 0.7, that's where we take that the 0.55 as our point estimate, and we add 0.15 to get 0.7, and we subtract 0.15 to get 0.4 on that other side. Okay, so our point estimate 0.55 is right in the middle, and we go up and down the same margin of error there. We might also just write it out without the interval notation, 0.4 to 0.7. So those are the main forms we present a confidence interval in. That margin of error that we come up with is constructed with some sort of degree of confidence, as well as the standard deviation of our sampling distribution for proportion, with a minor adjustment there. So that margin of error, we're going to have a degree confidence that is going to basically communicate how confident we are our population parameter falls inside that interval, and then that standard deviation going around our sampling distribution. So this confidence level describes how quote-unquote confident we are that the interval captures P. So let's talk a little bit more about that confidence level. Okay? So a confidence level is generally described as C%, where C represents the area between two z-scores we call critical values. So C, capital C, is going to be an actual number. It could be usually anywhere from 90 to 99 is going to be what C is. And that represents the percent, the area between two z-scores on the standard normal curve. Because remember, z-scores go along with the standard normal curve. So we're going to call these two z-scores critical values. And a critical value is the z-score that basically sets the boundary for our confidence interval, communicating how many standard deviations on either side do we want to go to get a certain degree of confidence. We label those critical values as z star. Okay? And we usually work with just the positive version of z star as you'll see, in a moment, but we label critical value as z star. Okay? So we have C% that communicates our confidence level, and we're going to have z star that communicates our critical value. And those two are related. C% is the area between the two z star values. Okay? Now calculating z star. We used to use a table. And in fact, on the AP exam for AP Statistics, you are still provided this table. And if you want to know a little bit more about how to use the table, you can definitely look that up. The table is a little bit more outdated because we have technology in our hands that can calculate z-star very easily. So I'm not going to talk about how to use the table in this video. I'm going to talk about how to use your graphing calculator. So on our TI-84s, you can calculate z-star by going to second, bars, and then down to number 3, inverse norm, which we've worked with before. So it should be pretty familiar to you. This is what pops up on the TI-84 CEs. On the TI-84 regulars or the pluses, it's going to look a little bit different, but we are going to put in a lot of the same information. So it's going to ask for an area, and that area represents the proportion in the area you are trying to find. And again, I'll show you exactly what I mean with the drawing here shortly. But it's going to represent the proportion of the area we're trying to find. The standard normal distribution, mu is always 0 and sigma is always 1 when finding critical values. So these two values are always 0 and 1 when you're finding these z-star values. The only thing that's going to change is the area, and for those who are using the CE calculator, it's also going to be the tail. Okay, where's the area you entered located? The area above, meaning the area you entered, where is it located? Okay, so let's take a look at an example, and I'm going to draw it out for you here so you can get a visual of what a z-star is. So let's say we want it to be 80% confident. We want to make a confidence interval where we are 80% confident that the parameter value falls in our interval. To get that degree of confidence, we have our standard normal distribution, and 80%, meaning we want the middle, the symmetric 80% right in the middle of our distribution. Okay? So remember what we know about normal distribution. So if we have 80% in the middle, okay, we have a z value that is going to be the upper and lower boundary. Now, since it's 80% in the middle, it's symmetric. So that means that z for above, the positive value is the same value as z below, just negative. Okay, so we have negative z star and positive z star. Those are going to be the boundaries, so 80% is in the middle. If 80% is in the middle, I know that 10% is in each tail of this standard normal distribution. Okay, so if I want to find z star, there are many combinations you can actually use to find the appropriate value on our calculator. And here are some of the ones you can put in. So if you have that CE, you have the option to choose where your area is. You could choose left, right, or center. So if you want 80% in the center, which is what our confidence level is, I put that in, and that gives me the negative Z star and the positive Z star. Notice those are the same numbers, just one's positive and one's negative. Okay. And I found my Z star value, which I'll need to create my confidence interval. So you can put that in, okay, 80% in the center. If you don't have that option for choosing the center, which some of the TI-84s do not, if you have an older version of the calculator, in the older version of the calculator, it always finds inverse norm to the left of some value. So if you put inverse norm of 0.1 to the left, that means you're looking at 10% to the left of what value? That's the question you're asking your calculator. What value is this so that 10% is to the left? And your calculator returns negative 1.28, etc. And that is another way to find your Z star value. Okay? And that's what you'll see me use a lot of the times in class, since a lot of the class sets don't have the CE. You could also just figure out 0.9 to the left. Okay? So 0.9 to the left is this value, where 90% is to the left of this value, right? The 10 plus the 80, 90% there, and that gives you the positive version of Z star. Okay. Now, I say it doesn't matter if you get the positive or the negative version of Z star, because in our confidence interval, we're just always going to use the positive version. Okay? You just want basically the absolute value of it. You want to just know what is the magnitude, how many standard deviations am I going up and down. And for us, in this example, Z star is 1.28. Usually for critical values, we do 2 decimal places. You can do 3 if you would like, and round that to 1.282. But a lot of the times you'll just see 2 decimal places. And that's our critical value. Okay, so that critical value corresponds to 80% confidence. Okay, let's do a couple more examples of this. So let's say we want to be 90% confident. 90% confident is 90% in the middle between a negative Z star and a positive Z star. So that's 5% in each tail. Okay. So on our calculator, we can do inverse norm. I like doing 0.05, always 0, 1. And then your tail, I put in left because I have 5% in my tail to the left of some value. And doing this, when I paste and press enter, it will give me my negative Z star. And I'm just going to write down the positive version, 1.65 or 1.645. And then I round it to 2 decimal places. Okay. Let's say we want to be 95% confident. Okay. 95% confidence, 95% in the middle, which is 2.5% in each tail. Now, hopefully this looks familiar because this is part of the empirical rule. If you remember the empirical rule, 68, 95, 99.7. We know that this should be approximately 2 because 1, 2, and 3 standard deviations out is our estimate for the empirical rule. When we do that, when we put the area of 0.025 into our calculator, just to the left, I'm going to get a Z star value of 1.96. Okay. So not exactly 2 like the empirical rule will tell us, because of course the empirical rule is an approximation, but we want to use that Z star value of 1.96. When we're making margin of errors and confidence intervals, this is usually the most common level of confidence we see. We'll see various degrees confidence, but this is probably the most common that you will see. And then one last example that we'll go up to is 99% confident. Same as before, 99% between our 2 Z values, 0.5% is in the tail. So if I put that into my calculator, that's 0.005. Remember that you're always putting this in as a decimal, not as a percentage. So don't put 0.5 there because it's 0.5%, which is 0.005 as a number. Okay, so don't let that fool you. And then that's to the left. So that gives me a z-star value of 2.58. Okay. Now, when we get into confidence intervals and actually constructing them, in the problem, they're going to tell you how confident they want you to be when you construct your margin of error. And what you'll be able to do is just use your calculator to find this z-star value. Okay. You do not have to draw a curve or show any sort of calculator work when you are constructing confidence intervals. Okay. I wanted to show you it now because we're learning about it, but you do not actually have to draw this curve every time you do a 4-step process. So this confidence level and this percent confident, let's interpret it a little bit more and talk about what we mean when we say percent confident. So like 95% confident, 99% confident. What does that actually mean? Well, the interpretation of it is a long-term capture rate. Okay? A C% confidence interval gives plausible values for a parameter. Okay? And the interval that we create is calculated from sampled data. That confidence level gives the long-term capture rate for basically calculating the confidence interval. So one of the ways we interpret it is we say in C% of all possible samples, the sampling method we used would yield an interval that captures the true parameter in C% of all possible samples. So that's the basic interpretation of what C% is. Your C% confidence is not any sort of probability. It's not a probability you captured the population parameter or anything like that. It is a long-term capture rate. So we want to make sure that we are going to be interpreting it correctly. Another way to say this is if we repeat this process many times and calculate a confidence interval each time, C% of them will capture the true parameter. So when we say repeat this process many times, we're talking about the sampling method. So in our introduction activity, if I were to repeatedly create a confidence interval to try to capture the proportion of green check marks in my population, C% of them will capture the true parameter. Here is a visual of this. Okay, so again, kind of referencing an open activity that we did. We would, every time we take a sample, we get a different value of p hat, which is going to result in a different confidence interval. So let's say 0.7. 0.7 was our population parameter p. And then this point right here, this is our point estimate. So in this first one, we got a point estimate of 0.5. And from that, we were able to create a confidence interval. And that confidence interval correctly captured our p value. Okay, you can see that right there in green. It is captured in our interval. The next one we created, our point estimate ended up being 0.9. And when we constructed our confidence interval there, we can see that we did not capture p. P is over here, and this is our endpoint. We did not capture p. And if we were to repeatedly take a sample of 10, find our p hat values, all of these points are our p hat values changing. And you can see that some of them, most of them capture it, but 2 of them in this example, in this simulation, 2 of them do not. So when we use our 95% confidence to create these confidence intervals, we mean that in the long run, we would expect 95% of these intervals to correctly capture our population parameter. And this is how we interpret our percent confidence here. Now, interpreting a confidence level, because that's what this 95% confidence is a confidence level, interpreting that and interpreting a confidence interval is going to be different. And we need to make sure that we know the difference between interpreting confidence interval and a confidence level. So I have little scripts that we commonly use to interpret both of these. So I'm going to give you those two things here, and then I'm going to give you examples using our opening activity. Okay, so the script for a confidence interval interpretation is we are C% confident that the interval from blank to blank captures the parameter in context. Okay, so we have filled that in with the information we have, which from our opening activity, we are 95% confident that the interval from 0.4 to 0.98 captures the proportion of check marks in our population. Okay, so we put what percent confident we are, we put what our interval is, and you can use any of the forms that we talked about at the beginning of the video. Any of those plus or minus ones, interval notation, or actually just writing out blank to blank. And then our parameter in context is very important. So that is just a confidence interval. Confidence level, what we just got done calculating and talking about, is if we take many samples of the same size from this population, in our example, 95% of them will result in an interval that captures the actual parameter. So this is like C%, whatever level of confidence we used. So interpreting a confidence level in context looks like this. If we take many samples of size 10 from our population of 100 cards, about 95% of them will result in an interval that captures the actual parameter value. So it captures the actual parameter value being the proportion of green cards, of green check marks in our population. Okay. So please make sure that you know the difference between confidence interval and confidence level. On any problem, you may be asked to interpret one or both of them, and you just got to know the difference between those two. Okay. Confidence interval is that set of plausible values for your parameter, and confidence level is that long run capture rate of the method. Okay, now that we've talked about our confidence level, meaning, and then how to interpret a confidence interval, let's talk about how we set up and find a confidence interval. The conditions for a confidence interval, because it's constructed with sample data, because it's constructed with p-hat, the distribution we use is the sampling distribution for a sample proportion. In our Unit 5 videos, I always talked about, hey, we're going to be using this for inference, and here it is, okay? The same conditions we had for the sampling distributions for sample proportions is what we have for confidence intervals. So this random independent normal, it's all going to look the same, mostly from sampling distributions. So for our random condition, we have to have either had a random sample or some sort of random assignment in an experiment. For independent, we want to check this 10% condition, and it still applies only when we're sampling. If we have an experiment, we don't need to check the 10% condition. We just want to make sure it's a well-designed experiment and that the treatment and control groups are independent of each other, right? And which would be true in a well-designed experiment. So we don't check that for experiments. We just check it for sampling. And then our normal. Okay, so our normal looks out slightly different from what we talked about in Unit 5. It's still the large counts condition, but because we don't have what our population parameter is, we don't know P, that's why we're taking sample data to find it. Instead of using P to check the large counts condition, we use p-hat. So we are making just that slight adjustment, but otherwise everything else is the same as it was in sampling distributions, okay? So again, your large counts condition, we use p-hat because we are constructing our confidence interval around our point estimate of p-hat. Okay? That is our center. That is what we are constructing it around. So that is going to be what we check for normality. We want to make sure that there's enough successes and enough failures in our sample to say that the distribution will be approximately normal. Now, from here, when calculating our standard deviation of our sampling distribution, we used P for our sampling distribution, but because we don't know P from our population, our only other option is to use P hat, what we get from our sample data. Now, because we're using P hat instead of P when calculating our standard deviation, we changed the word slightly into standard error of our sample proportion. Okay, so from standard deviation, we're going to talk about the standard error. And the standard error describes how close the sample proportion P hat will be to the population proportion in repeated SRSs of size n, whatever your sample size is. So that's going to be our interpretation of standard error. Now, the way we calculate it is the same as we did for sampling distributions. It's just instead of using P, we have to use P hat. So remember the standard deviation of our sampling distribution for a sample proportion. Okay, this is what it was in Unit 5. Okay. Now, we replace the P with the P hat, and that introduces some error into our calculation because we've said before, P hat changes with each sample you take. And because of that error, we call this standard error of our sampling, of our sample proportion P hat. It's quite the mouthful. So I write it SE sub P hat. Some people also write just like SE and then in parentheses P hat as the notation, but it's just a notation to describe the standard error of P hat. But we're going to use that to calculate our confidence interval. And we've come up with all the components of our confidence interval. Now it's time to put them all together. So when all three of those conditions we just talked about are met, a C% confidence interval to try to capture the unknown population proportion P is P hat plus or minus Z star times that standard error. Okay, we have our point estimate plus or minus our critical value times the standard error of P hat. Okay. Z star is that critical value for the standard normal curve with C% of its area between negative Z star and positive Z star. Notice the formula always uses the positive version because we're doing the plus minus. So whether we use positive or negative, it really doesn't matter because we're going up and down the same amount. So Z star represents how many standard deviations above and below we want to go to be C% confident. And so this is number of standard deviations, and then this is actual standard deviations, the actual unit based on our sample data. This inference procedure, this is called a one sample Z interval for a proportion. Okay. And this is our first inference method, so this is a big deal. All pieces of those of that name is important because what we're going to be doing when we learn about all of these different inference methods, we always want to name them correctly. So right now we're dealing with a one sample. Okay, we will also be dealing with two samples. Okay, so 1 and 2. So you need to make sure you identify that this is a one sample. We're doing a Z interval. Okay, we are also going to be looking at T intervals in the next unit. We have T intervals, we have a Z test, and we're going to have a T test. Okay. So we have a few different things we're creating. We want to make sure we identify this as a Z interval. And then we're doing this for a proportion. We are also going to be doing it for means in the next unit. Okay. So we call it a one sample Z interval for a proportion. You can also call it a one prop Z interval. Okay, which prop is proportion. One proportion Z interval is another way we say that. Okay, but we want to communicate that inference. Okay, and we're going to finish today with an example using our 4-step process. Okay, so we'll walk through this one example to finish up the notes for today. So a recent survey wanted to see what proportion of high school students believe there's life on Mars. The poll's population was all American high school students, and they selected an SRS of 430 students and found 204 of them believed that there is life on Mars. So we are going to construct and interpret a 96% confidence interval for this proportion. Okay. So our 4 steps. Remember, our 4 steps are communicate, conditions, calculate, conclude. Okay, so there's going to be our 4 C's essentially here. So first up is communicate. We want to communicate what our parameter P is in the context of the problem and write down the confidence level we are using. So P in context. P is the proportion of high school students who believe there is life on Mars. So we write that down in words. We want to write down our confidence level, which is always given in the problem. And then this is also a good step where we write down what Z star is. So Z star, if I want to be 96% confident, that means that I have 2% in each tail. So if I do inverse norm of that 2% tail probability, those stay the same and it's to the left, I can get what my Z star value is, which in this case is 2.06 for a 96% confident. Notice I didn't draw a curve. You can if you want, but you don't have to. And we don't want to write down any calculator speak either. That's not necessarily showing work. We can go from C% being 96% straight to Z star equals 2.06. And this is also a good spot to communicate what our P hat value is, since we have to use that in our calculations as well. So P hat, 204 out of 430 students believe that there is life on Mars, and that gives us 0.474 as our proportion. So that's step 1. That is communicating some information from the problem. Step 2 is going to be the conditions, where we want to check the conditions required, being our random, independent, and our normal conditions. So a random sample was taken. Perfect. Okay. You are probably always going to, when you do long inference problems, you are probably always going to have a random sample. So it can feel a little redundant to write this down when it's something that's given in the problem, but you need to. You need to communicate that you know that this has to be a condition in order to perform accurate inference. Okay, so write it down. A random sample was taken. Perfect. That's all you got to do. For independent, we want to check our 10% condition because we did sample. So we're going to check that our sample size is less than 10% of our population. And as we had before, our population is usually given in words instead of a value. So 430, less than 10%, all high school students. It's a safe assumption, so we're going to assume that this condition is met. Our last one is our normal condition. And you don't actually have to calculate these values, but you want to plug them into that large count condition, where we check to see that 430 times 0.47, and I probably should have written a 4 right here to be like totally correct, and 430 times 0.526 to be totally correct. Just because the P hat value, I do want to be consistent with my P hat value, so I'll change those. But you put them into your large counts condition, you can see that they are both true, and we say that that condition is satisfied. Okay. Step 3 is calculate. We want to identify our inference method and construct a confidence interval by writing down the formula values substituted into the formula, and then just conclude with what our interval is. So when we write down our inference method, we want to say this is a one sample Z interval for proportions. Okay? This is the only inference method we have right now, so that's fine. Easy. This is the only one you know. Okay. You can also write down the formula. So on the AP exam, they do give you a formula sheet. We'll talk a little bit more about that in the next set of notes. But on that formula sheet, they don't specifically give you this formula. What you'll have to do is pick out pieces from that formula sheet, put them together to construct this interval. So on the AP exam, what they say is you want to identify your inference procedure, and you can do that either by naming the test or by writing down the formula with the correct symbols. Okay. So technically, you only have to do one of these. What I would like to see is that you do both. Okay. do both. We're learning. It's helpful to be redundant in some of our work as we are learning it. So I want you to write down both the name as well as the formula for these inference procedures. Okay, but we plug everything in. Notice that we do have our p hat value. Okay, we do have our z star value, and we do have our value for n. So we're going to show those values substituted into that formula. And this is what it looks like. Okay, substitute those values in to their correct spots to calculate our confidence interval. Once you show the work for the confidence interval by substituting in the values, you don't actually have to show any algebra. You can if you want to. If you want to work it out by hand, that's totally fine. But from here, you can jump straight into what your confidence interval is. So if you're finding it out by hand, I keep this the same. I keep the plus minus, and then I do this part in my calculator. So I'll enter into my calculator 2.06 square root this value times this value divided by 430. Okay, you enter that into your calculator to get that margin of error. And this is what I got. So I get this plus or minus, and then this is the value I get from my calculator. Okay, and you're welcome to leave your confidence interval just like that. There is nothing wrong with communicating your confidence interval like that. Or you can write down interval notation. So interval notation would be taking this 0.474 and then adding this value to get your upper boundary, and then taking your point estimate, subtracting this value to get your lower boundary. We'll talk about how to do this on your calculator in the next set of notes. And your calculator will give you your confidence interval as interval notation as well. The last step here is our conclude step, where we want to interpret this interval. So this is using the script I gave you earlier, just in the context of the problem. So we would say we are 96% confident that the interval from 0.4244 to 0.5236 captures the true proportion of high school students who believe there is life on Mars. So we say we are C% confident that the interval from this to this captures the true proportion of, and then we want to put the context to it. If you don't have context to it, you will not get full credit. If you just end it here, even if you use those numbers, you will not get full credit for this interpretation. A whole thing of statistics is putting context to the data. So you have to make sure you put that context to the data. And that wraps up today's lesson on confidence intervals for proportions. Thank you guys so much for following along. If you are interested in continuing this series, our next video is going to talk about the margin of error, how to find it, how to work with it, and the delicate balance between margin of error, confidence level, and our sample size. Thank you guys so much for following along again. If you enjoyed this video, please remember to hit the like button and subscribe to my YouTube channel for more AP statistics content. I wish you endless statistical success, and I will see you in the next video.